Hello and welcome to the course of Introduction to Astrophysical Fluids. So, we just discussed that how the distribution function in the mu space can also obey the Liouville's equation, and from that we also obtained so called Vlasov's equation or collisionless Boltzmann equation. I said that if you just remember that the equation should look like that, that is del f del t plus u dot gradient of f plus f by m dot velocity space gradient of f should vanish, and I said that this is only possible when the system is collisionless. If the system is collisional, if the system has collisions, then the right hand side will no longer be 0. And how should the right hand side be looking like? There is no unique response for that, unfortunately, but from case to case we can try to model the collisions. Before doing that, let us first understand one conceptual thing, that there is no collisionless system in nature. Okay. This is just an idealistic approximation. Okay. Collisionless. What happens in reality? We have only weakly collisional system and strongly collisional system or collisional system normal. Okay. Now, how to quantify that? I mean, how to really define in a proper way that which system is collisional and which system is weakly collisional and which system is strongly collisional? Do we have a way for that? So, in kinetic theory, maybe you have learned the concept of mean free path. So, mean free path is nothing but the average path traversed by one particle between two successive collisions. So, from that you can easily understand that if this mean free path basically in a given container is very large with respect to the accessible space for moving of the particles, then the system can be thought to be weakly collisional. Okay. That means, the most of the time the particle is moving without collision. Okay. So, for example, that you have a box and the box is consisting of particles, and we say that n is the number density of the box. So, n particles will be in unit volume, that is the definition of the number density. Then one particle will have 1 by n volume. Okay. So, we have to understand what is the meaning of weakly collisional system and strongly collisional system, and actually how can we distinguish one from the other. Let us take for example a dilute gas type of system where the gas molecules are very distant from one another. Okay. So, for such type of system you can easily understand that the effective volume of one particle, which is nothing but 4/3 pi times a cube, where a is the radius of one particle, will be much less than the available space for the particle. Now, how to calculate that? There is a very elegant calculation for that. You can think that if n is the number density of the system, then n particles will have unit volume, then one particle will have 1 by n volume. So, that is the volume accessible for the system, okay, given the container. Okay. So, if I just give you a container and the gas molecules are constrained to be in the container, then 1 by n will be the volume which is available for one single particle, given n is the number density. Then the condition for the system is weakly collisional if 4/3 pi a cube should be very less than 1 by n. Okay. And then you can easily say that 4/3 pi a cube n should be very less than 1. Okay. So, you can say that pi n a cube should be less than 3 by 4, right, which again is less than 1. So, pi n a cube is very less than 1. So, if you know the molecular radius or the particle radius, sorry, every time I say, because I am thinking of gas molecules, but gas particles in general, and if you know the number density, then basically you can see whether the system is weakly collisional or not. Okay. Now, another way of seeing whether the system is weakly collisional or not, that is, if you have learnt in kinetic theory the concept of mean free path. So, the mean free path basically is the average path traversed by one particle of the gas between two successive collisions, right. And if you remember, a very rough approximation gives quantitative formula for mean free path lambda, which is equal to 1 by the number density times pi times a square, okay, where a is the particle radius. Okay. Then just by multiplying both numerator and denominator, you can have this, and so lambda by a will simply be 1 by pi n a cube, and as pi n a cube is very less than 1. So, lambda by a will be very greater than 1, because this is 1 by pi n a cube. So, lambda should be very greater than a. It simply says that a system is weakly collisional if the mean free path is very large with respect to the molecular or the particle radius. Okay. In the same manner, if the mean free path is of the order, or even it is not very large, but it is just moderately large with respect to the molecular radius or the particle radius of the system, then the system can be thought to be collisional or moderately collisional. Okay. So, a dense gas, for example, is an example of a collisional system. Okay. Now, the question is how to model collisions. The answer is there is no general recipe. However, we can model the collisions if the particles collide with each other by elastic collisions. That means that every single particle will be considered to be as hard, rigid sphere type of thing, okay, and no source of dissipation. So, no energy will be dissipated, and actually I have to say that the kinetic energy will be conserved before and after the collision. That is the definition of elastic collision. You all know that linear momentum is conserved in any type of collision, whether collision is elastic or non-elastic or inelastic or partially elastic, but kinetic energy is conserved only in the case of elastic collisions. Okay. So, basically we are taking the case where we have two conservations, one is the linear momentum conservation. So, we have linear momentum conservation and kinetic energy conservation before and after the collision. Okay. Firstly, now to model. Firstly, we estimate the number of collisions I call that delta NC per unit volume, okay, per unit time. Those things are important, per unit volume, per unit time, number of collisions, okay, which deflect particles into a solid angle d omega. Okay. That is also important. Now, what is the picture for that? Let us say this particle is coming from this direction, okay, and this particle is coming from this direction, okay, this one. Now, when they meet over here, okay, let us say they collide, okay, then after the collision the new particles will go, let us say, here and here, for example. Okay. So, for example, if it was u1 and it was u, okay, then this one, let us say u1 prime. So, this one got deflected into this and this one deflected into u prime, okay. And someone, let us say, is counting that how many particles are coming into this direction, because whether the particle will come in. So, basically just keeping the momentum conservation intact, the two particles can go like this and this, and also can go like this and this, also can go from this and this, okay, all are possible. So, someone can put a detector which just calculates the particles which are deflected after the collision in a solid angle, which is d omega, and we are interested in calculating that. So, delta NC will be the number of collisions per unit volume, per unit time, and deflects the particles into a solid angle d omega. That means, those collisions which causes one of the particles to deflect in a solid angle d omega. Okay. Now, how to do that theoretically? Well, we have to start from very simplistic assumption. Let us suppose we have two particle beams. Okay. We have two particle beams, one should look like this and another should look like this. For simplicity, we just take like a homogeneous cylinder type of thing, and one is just full of particles having velocity u and with number density n, another is of, so this is a deep blue color particles. This tube has a number density n1 and velocity u1. Okay. I call this one as beam 1 and this one as beam 2. Okay. Now, we say that if we try to understand what is happening to an observer which is sitting on this. So, the observer is here, Okay. Then to every particle of this beam some observer is attached, basically that is the equivalent thing of saying that observer is placed on this beam. Okay. So, every particle of beam 1 will experience a flux of particle I will be equal to simply u minus u1 times in 1. Why it is that? Because these particles are having or experiencing a velocity, an incoming velocity of the second beam or beam number 2 with a velocity u minus u1, right. Of course, you know that if they are basically, I mean the two velocities are in reality, if they are just heading towards each other, that will be simply the sum of the two, right. Okay. But they are nothing but, I mean vectorially written, they are nothing but the vector difference of the two. Okay. So, u minus u1 modulus times the number density of the second beam, that will give the flux of the particles which are experienced by every particle of this beam. Okay. Flux is nothing but, so flux is nothing but density times velocity, so to in u type of thing. Okay. So, this is the flux. Okay. So, of course, another way of saying that flux is nothing but the number of particle per unit time per unit volume, that is another way of saying. Okay. So, that you can always say, not really per unit volume, but I mean the per unit area, basically perpendicular, that is why this Nu is I mean. So, okay, flux is density times the velocity. Okay. Another way of defining flux is nothing but number of particles per unit time per unit area. Perpendicular to the direction of particle flow. Okay. So, that is the definition of flux. Okay. So, you can easily see that I will simply be, I is the number, the flux of the particles experienced by every particle of this beam will simply be this one. Okay. So, now we understood what I is, that is the flux of particles, okay, in from the incoming beam 2 with as experienced by every particle of beam 1. So, now we can easily say from common sense that delta NC, which is the number of collisions per unit volume per unit time and deflecting particles into a solid angle d omega, will simply be proportional to I. Okay. Because if the flux of the particles are greater, then of course, the number of collisions will also be greater, right. Again, del NC will be proportional to N. That means, if the number density of the particles of the observer beam, that means where the flux of the particles are coming into, okay, if that is more and more, I mean greater, then again the number of collisions are greater. Okay. And finally, del NC is proportional to sigma star omega d omega. So, sigma star omega d omega is nothing but the probability distribution. So, this is nothing but the probability distribution function as a function of omega. Okay. So, finally, by the law of or rule of joint variation, you can easily say this is exactly equal to sigma star omega n times I d omega times a constant of proportionality. Okay. Just remember that when I say this one is true, then n and sigma star omega d omega are kept constant. When this one is true, then I and this one is kept constant. When this one is true, then the other two factors are kept constant. But when we are saying that we apply the rule of joint variation, then all the three factors will vary, or rather can vary. Okay. Then you can easily see that this is nothing but n times n1 u minus u1 mod sigma omega d omega, where I simply redefined my sigma omega as a times sigma star omega. Okay. That is another, I mean, just a nomenclature. Okay. Now, finally, our goal is to derive the Boltzmann equation for collisional systems. Okay. Now, for collisional systems, the first physical thing we have to think is that here the F. So, for collisional systems, so I am just first make this one within rectangle, this result, then I start that for collisional systems, basically F, that is the distribution function, does change with time. So, that is something very important. For collisionless system, we do not have df dt, right. Okay. Thank you.